Alright, welcome to lesson 1.10. Today we're going to identify how changes in constants of a quadratic function written in vertex form affect the graph of the function. So a lot there from way back in the day, in particular vertex form, and so we're going to take a little bit of time to kind of reestablish what vertex form is, why it's so useful, and then to talk a little bit about transformations. So if you've forgotten what transformations are, it might be worthwhile taking a little Google search to transformations to kind of refresh your memory with the language of transformations, because we're going to be using them a little bit here. Alright, so to start off, by completing this problem, you're actually going to sort of rediscover what vertex form is and why it's so useful. So go ahead, copy this down, copy the rough sketch of the graph down, doesn't need to be super perfect. And then go ahead and answer questions A, B, C, and D. This should take you, about maybe 5 to 7 minutes or so, maybe 10 if you need to. And what you'll notice is something that you probably learned maybe 2 years ago, but may or may not have forgotten. Alright, so just as a reminder, I'm going to check for your work to this problem. So if you struggled in a couple of places, hopefully my hints will enable you to get back on the right track. But essentially we have these two different functions, f and g. And g is graphed over here to the right. In the first part, we want to find the roots and the vertex of f of x. So finding the roots, and this is all review of course, we set our function equal to 0 and solve for x using the quadratic formula. And you're going to find that the roots are in fact complex values. So we know that the function will not intersect the x-axis. And then the vertex is found actually while finding the roots, right? We see that negative b over 2a is going to end up giving us an x value for the vertex, an x value of 2. And I'm going to write it as a coordinate point because you need to find the y coordinate as well. So you know that the x value is 2, and if you plug 2 in, you get 2 squared, which is 4, minus 4 times 2, which is negative 8. So 4 minus 8 is negative 4, and then negative 4 plus 9 is positive 5. So the vertex is the point 2, 5, and we have complex roots. So I'll just write CR for complex roots. Okay? Prove that f and g are the same function. So there's a couple ways that you could do this. To show that two things are the same, you need to show that they are completely identical. Well, you could try and take f of x and make it look just like g of x, or you could try and take g of x and make it look just like f of x. I personally think it'd be much easier to just FOIL out x minus 2 times x minus 2. But if you really wanted to, you could complete the square for f of x and go that route. But what I would recommend doing is squaring out x minus 2 times x minus 2 by FOILing, and you'll see that you get the exact same thing that we have for f of x. And so since they are both exactly the same, they must be the same function. Now just a reminder, I'm going through this quickly. Your work should already be down for these problems, and if you find that you didn't complete all that work, you should pause and make sure that happens. Alright, which form of the function, f or g, gives you more information about the function? And the hint that I gave you here was to look at that vertex again. So look at what the vertex for f was, 2, 5. Why don't we plot that point? Well, x value of 2, y value of 5, and notice I'm right here. Okay, great, that makes sense. G and f were the same function, so the vertex for both should be the same. But now let's look at our two functions, f and g. Notice that in g, the constants are actually 2 and 5. Well, that's interesting. 2 and 5, those are the x and y coordinates of our vertex. And so what you might imagine is that g of x is actually giving you some information about the vertex of our function g of x, just in the way that it's set up. And so g of x, in fact, this is called vertex form, is telling us the coordinate points for the vertex of our function g of x. Alright, now the last one is, what would you have to do to our function in order to ensure that it has real roots? And how would you do this algebraically? So you might imagine if you want this function to have real roots, it needs to intersect the x-axis. In other words, you need to bring it down or shift it downward, or the word that we use mathematically is translate. So we would translate the function downward. Now how many units would you have to translate it downward to intersect the x-axis? Well, you'd have to translate it at least 5 downward, but anything more will work too. So you could translate it downward, let's say, 6 units. How would you do this? Well, notice that if you're translating it downward 6 units, what you're doing is you're making every y value in your function, every y value go down by 6. In other words, you're just taking your function and subtracting 6. So your new function would be x minus 2 squared plus 5. And now we want to translate it down 6 units, so we'd subtract 6. Well, notice how easy this is to write. Now we just have x minus 2 squared minus 1. What is the vertex of our new function? Oh, yeah, very easy. 2, negative 1, which is exactly where we'd expect it to be if we were to translate our function down 6 units. All right, so now that you've rediscovered vertex form, let's make sure we have it defined and clearly understand the advantages and disadvantages of having an equation in vertex form. All right, so here are the different forms that we can write quadratic function. The first is standard form, and we've seen this before. And the way that we write it is ax squared plus bx plus c. In other words, what you've done here is you've fully kind of multiplied everything out. And it's standard form. It's what you most often will see a quadratic function written in. And then we have vertex form, which is written as a times x minus h squared plus k. And you'll notice as I wrote this a value in green here because this a value is actually the same for standard form and vertex form. What you can imagine is that for vertex form, you could square this out and then multiply the a into whatever you get from foiling, and then add the k value to whatever the constant term that you get from foiling this out is, and what you'll end up with is standard form all over again. Well, in doing so, what you'll end up with is x squared times a. So in other words, the a coefficient for each vertex form and standard form is going to be exactly the same. And let's talk a little bit more about standard form. Why is it so helpful? Well, standard form is helpful because it allows us to use the quadratic formula really easily. So if I set this function equal to some value, maybe 0 for example, or I could set it to equal to 5 or 7, it lends itself really easily to the quadratic formula. As long as I then eventually get it set equal to 0, I can solve for x easily. I'll say there that a plus or a pro to the standard form of a quadratic function is that it's easy to use the quadratic formula. Now let's look at the vertex form, and there's a lot of pros here. Obviously a con is that it doesn't really set up very nicely for using the quadratic formula, right? I'd have to square this out. So that's kind of a bummer. But it does show me some really cool things. The first is that the vertex, and we call it vertex form for a reason, the vertex of our parabola is at the point h comma k. Alright, so there we have the vertex of our function f is h comma k. Notice not negative h, but the positive h, right? H comma k. And the overall idea of vertex form is that it actually makes it really easy to visualize what our parabola will look like. And the reason that is that we have built into vertex form the transformations that are made to what's called the parent function, or just our standard basic function. So the standard and easiest quadratic to use would be a function f of x is equal to x squared. And the vertex form is really just a series of manipulations to our standard form parent function x squared, where we are showing exactly what we are doing to our parabola in order to get our new function. So you can imagine if I were to add, say, plus 3, if I added 3 to my function, well, that would do what to my standard parabola, x squared? Well, just think about it. It would increase each y value by 3, and so my function would shift up or translate upward 3 units. So the k value here will help you understand the translation either up or down. And as we're going to find out in a second, the h value is going to also inform you about some transformation, and the a value will inform you about a particular characteristic or characteristics of your function as well. So we're going to discover that in just a minute, but what we want to just write down here so that we don't forget to come back is that the vertex form allows us to visualize our function using transformations. So basic idea is standard form, it's really easy to implement the quadratic formula in order to solve. So standard form is very easy when trying to solve a quadratic, but vertex form is really helpful in visualizing what the function will look like by thinking about the transformations to my basic x squared function. Okay? In other words, there are built-in pieces of my vertex form which are just going to sort of tell me what my parabola looks like. And the most obvious one, of course, is the vertex, which is really built into the vertex form, hence the name vertex form. All right, so what we're going to do now is kind of explore the different ways in which the vertex form helps us visualize our parabola, and especially thinking about the different transformations that are built into it. Alright, so to understand the vertex form of a quadratic, it's helpful to graph a couple of different variations of it where we're only changing either the a, h, or k value. So that way you can really clearly in your mind picture how changing that one value will affect your very basic parabola. And so to start off, just sketch the graph of y equal x squared. This is the most basic parabola, most basic quadratic function, and so for that reason it's called a parent function, and we'll see this term come up in the second unit as well, so it's good to just start getting prepared for it. And notice here that this is a function in vertex form, right? Notice that the h and k value, well, the h value is 0, the a value is 1, and the k value is 0. And that's how you end up with just x squared. So right off the bat, as I'm sure you can visualize, the vertex is very simple. H value of 0, k value of 0, right? And so now as you go through and you work through number 2, number 3, number 4, and you graph these different functions, you'll notice how your parabola is changing from the parent function based on these different things that you're doing to either your k, h, or a value. Okay? A couple of words on how to sketch the graphs of these functions. You already know that the point h, comma k is the vertex, and so you can use that to your advantage. Plot the vertex, and then you can just use make a table of x and y values where you choose some x values to the left and to the right of the vertex and find what the y values are by plugging them into the function. Just things that you've obviously done many, many times over. And if you need to check what your graph looks like, you can always go to your calculator, or if you don't have a calculator, you can go to wolframalpha.com. I'll write that out for you. wolframalpha.com. That's wolframalpha.com. And if you want it to sketch the graph of a function, you can just type into the search bar graph, and then whatever function you want it to graph. In fact, you can have it graph as many as you want by writing graph, a function, another function, comma, another function, so on and so forth. Okay? So use that to your advantage. Make sure that you've done 1, 2, 3, and 4, all of them, so that when we come into class tomorrow, we'll be able to have a discussion about what the a, h, and k values, what they have, how they affect the parent function, and then we'll be able to go ahead and move into our task for the day and understand more deeply how this can help us look at quadratic functions in greater detail.